In this module, we'll be looking at confidence intervals that we use in simulation modeling and analysis. And in particular, for this module, we'll focus on confidence intervals on the mean mu of a random variable. Now note that we're not doing a theoretical development. Instead, our purpose is to look at confidence intervals from an application standpoint and then look at how we use those to guide our simulation experimentation. For a theoretical development, you should see your favorite introductory book on probability and statistics, and it's a fairly well-covered topic. So we're going to use an example model. We're looking at the registration desk at a healthcare clinic. And so we see that we have patients arriving randomly, and they wait in line in the queue for the registration desk attendant who registers them for the clinic, and then the patients depart. We have a single registration desk, and so what we have is a single server queuing system. And we're interested in three basic things. We're interested in, for the first 100 patients, the average time in system. And that's the time from when they arrive until they depart registered, or so they go into service from the clinic. We want to know the maximum queue length over the first 100 patients, so the maximum number of entities that are waiting in line while the system is operating. Again, for the first 100 patients. And then finally, we'd like to know at what time of the day does the 100th patient complete registration. So let's focus on this first random variable, x. And so we know that because the arrivals are random, we know that because the arrivals are random and the service is random, that the values that we're interested in are also random variables. And because they're random variables, we also know that they have some probability distribution. So if we have x, f of x, we just don't happen to know what that is. So we're just going to draw a distribution here. Again, no notion of what that is. And for this video, what we're interested in is estimating this value mean, mu, and we also have the standard deviation. And so we're interested in estimating this value of mu. And so the way we do that in our simulation is we generate observations. So we run the simulation, and then we generate observations of our random variable x. And so we end up with observation x1, observation x2, to observation xn. And from these n observations, we want to estimate this value of mu. And the typical way that we do that is we use the sample mean, x bar n, which is simply 1 over n times the sum of xi. I equals 1 to n, right? And so this x bar n is our estimate of the mean mu. Now, this is what's called a point estimate. So let me put that here. And we know a couple of things about this point estimate. We know that as we increase n, we're getting a better and better estimate of mu. But what we don't know is for a given n, how close or far from the true mean mu our estimate is. So for example, our estimate x bar n might be right here, or it might be right here, or it might be right on the mean. We simply don't know where that value resides. And so what we want to look at from a confidence interval standpoint is how we can get some additional information about that location, or the potential location of our estimate x bar n. Now, because the individual xi values are observations of a random variable, that also tells us that the x bar n is also a random variable. And so it also has a distribution. So now if we look at the distribution of x bar n, f x bar n, it also has some distribution. And again, we don't know what that distribution is, but we'd like to know. Now, this value, the mean, is exactly equal to mu. Okay, we know that because the values, because of the way we computed the sample mean. What we don't know is what this variance term is. So if we look at the variance of x bar n, we really don't know about that, but we'd really like to know about that because that variance of x bar n gives us some information about where, with respect to the true mean mu, our observation could be. Now, if the xi's are independent, so if the xi values are independent, this is important, then it turns out that this variance of x bar n is equal to the variance of x divided by n. So if we know we have independent observations, then we can in turn estimate these values, because we still don't know sigma squared, but we can estimate sigma squared using the sample variance. So we have s squared 1 over n minus 1 summation of xi minus x bar n quantity squared. So just the normal expression for computing the sample variance. And so this sample variance term leads us to something called the standard error, which is simply equal to Sn divided by the square root of n. And this standard error is what is going to provide us information about the potential location of our estimate with respect to the true mean. So before I continue, let me fix this. I noticed when I was reviewing the video that you can't actually see all of it, so let me just go back and put it over here. This is s squared is 1 over n minus 1 times the summation of the individual xi minus x bar n quantity squared. And so that leads to our standard error term. And something interesting about the standard error, if we look at this value, we know that as n gets larger, our estimate of this standard deviation gets closer and closer to the true value of sigma, while n continues to grow. And so that tells us as n grows, the standard error shrinks, because we are taking a estimate of a single value and we're dividing it by an increasing number. And so the the standard error we can control by simply increasing the value of n, the number of observations that we have. And so this leads us to the approximate 100 times 1 minus alpha % confidence interval on mu is as follows. X bar n plus or minus t. Let me do a better job of making a t here. T n minus 1, 1 minus alpha over 2 times the standard error. Square root of n, where this is the 1 minus alpha over 2 percentage point on students' t distribution. So this is students' t distribution. Again, we're not particularly interested in the theoretical development of this. Look in your favorite introductory textbook on probability and statistics, and I'm sure you can find the details. What we are interested in is how this value, we use this value to be more confident about our estimate of mu, which is x bar n. And so as with the standard error, as with the sample standard deviation, the t statistic, the t statistic value will converge to a number as n increases. So as the number of degrees of freedom increase, this t value just converges to a number. So we have a number, we have something that converges to a number, times something else that converges to a number, divided by square root of n. And so we are in control of this value, which is called the half-width of the confidence interval, h, half-width, by simply increasing the value of n. We can control the confidence interval half-width. And the confidence interval as computed here is what's called an interval estimate. Interval estimate. So our x bar n, as we've said before, is a point estimate. The confidence interval is an interval estimate. And those two things together we use to determine how many replications of our simulation we need to run. In other words, how many observations do we need in order to be confident about our estimate of mu. So next, let's just look at a really simple example. So here we have 10 observations of the 3 random variables of interest to us, which again, x represents the time in system for the average time in system for the first 100 patients, y represents the maximum queue length, and z represents the time in hours, starting from when the first patient arrived till when the 100th patient arrived. And recall our confidence interval, oops, let me grab the pen here. Our confidence interval is x bar n plus or minus t n minus 1 minus alpha over 2 times Sn over the square root of n. And so we're just going to use Excel to compute those values. So let me just do that here. The first thing we want is the average. And so we can get the average just using Excel's average function. So there's our x bar n term. We can also get the sample standard deviation. And we're going to use Excel's stdv function. And we just give it our 10 observations. We can get the t statistic, t inverse, and it asks for the probability. And for when you use Excel, note that instead of using alpha over 2, we simply use alpha. So our 1 minus alpha over 2 means it's the upper percentage point, but Excel already corrects for that for doing this two-tailed test, so we're going to use 0.05. And our number of degrees of freedom are 9 in minus 1. Oops, let me move that over. Put it right here. This is our t statistic. And then we can compute our confidence interval half-width is simply the t statistic times the standard deviation divided by the square root of 10. Now, the square root of the number of observations. And so this h represents this confidence interval half-width. And we can now compute our confidence interval, the lower and the upper, by simply saying the lower value is the sample mean minus the half-width, and the upper value is the sample mean plus the half-width. And so our confidence interval is from 0.414 to 0.738. And what this tells us is that we are 95% confident that the true mean falls within these two values. So 2 observations to close this video. First of all, note that because of how we computed the confidence interval, as we said before, we're in control of this confidence interval half-width. So we can compute this, we can run additional replications and increase the value of n and make this value h smaller. And as we make that smaller, then the width of this interval between our lower and upper bound gets smaller and smaller, and we become systematically, or we become more confident about our estimate of the value mu. Secondly, and we'll see this in the next video in this module, by the way. Secondly, one comment about something that the confidence interval is not is that it's common for people to think of this in terms of probability. In other words, they want to make the statement that there's 95% probability that the true mean mu is between this lower and upper value. And that's definitely not true. Where there's difference between confidence and probability. And so the true mean of our distribution x is a number. And so the probability that it's on this interval between L and U is either 0 or 1. In other words, it's either in that interval or it's not. So there's no probability here. What the confidence tells me, if I replicate this experiment many, many times, so if I sample 10 more observations, compute the confidence interval, then 10 more and compute the confidence interval, and then 10 more and compute the confidence interval, 95% of those experiments will cover the true mean. So we can't make any type of probabilistic statement about where the true mean is with respect to these particular values. And that's really the fundamental difference between talking about confidence and talking about probability. So in the next video in this module, we will look at implementing this in Simio, and then we will look at this characteristic of being able to reduce the confidence interval half-width, in other words, increasing our confidence simply by increasing the number of replications.